Thank you very much for inviting me to this workshop. I'm really honored to be here. I'm Morio Toyoshima of National Institute of Information and Communication Technology, NICT in Japan. So today, I would like to present my talk on recent trends of space data communication and the future prospects. Here is outline of my talk. First, I introduce the features of space data communication. Then, I will describe about Japanese space data communication mission in this talk. So, including these missions. Then, I conclude my talk. So, advantage of space laser comm includes several aspects. The first one is, of course, large communication capacity. So if we want to send 80 gigabyte data, so it takes about 16 seconds by optical when we use, for example, 40 gigabits per sec. So, but by using RF, it takes about 13 minutes. So 50 times wider area can be transmitted via optical link. So of course, the optical antenna is very small, like 20 or 10 centimeters. And in order to send the same data rate by RF, the antenna size of RF will be 1 or 2 meters. So size of data terminal is very small. So low vibrational disturbance can be realized against precision sensors. And also, lasercom has a highly secure communication aspect. For example, if we compare RF at X-band, so if we send X-band from low altitude, so the footprint on the ground is about 3 or 4 kilometers. On the other hand, by using laser communication, the footprint will be 10 or 20 meters. So it has low probability of intercept and low probability of detection. So it is very secure. So here are the features of space laser communications. Advantages are a large communication capacity, low vibrational disturbance due to smaller, lighter, and lower power consumption, and also highly secure communication, and there is no regulatory restriction. But there are some disadvantages because laser terminal requires higher tracking accuracy, and there is optical scintillation effect due to atmospheric turbulence, and the optical link can be interrupted by clouds and rain. However, optical technology is expected to revolutionize space system architecture in the future. So here is the data rate trend for space laser communication verified in space. This shows the launch year. This shows the data rate. So for the first decade, the data rate increased by a factor of 1,000 per 10 years. After the next decade, so the demonstration become twice double. Then maybe in the future, data rate will be drastically increased because WDM technique or higher order multiple modulation can be possible. And also, the other screen, so data rate is not so high, but the usage for microsatellite is like this here. So I will describe space data communication missions in Japan. The first engineering test satellite 6 was launched in 1994. We demonstrated world first laser communication experiment between a geostationary satellite and ground. So here is the spot from the geostationary satellite, and here is the spot for the uplink laser beam. So this is the laser communication terminal. At that time, 1 megabps was transmitted. Here is our optical ground station with 1.5 meter telescope. After that, we collaborated with JAXA. So we demonstrated first LEO to ground laser communication experiment by using OISET satellite. So I was in charge of development of laser communication terminal when I was in JAXA. So here is a bright spot from the OISET satellite. So at that time, 50 megabits per sec was demonstrated. So after that, we have launched microsatellite, which embark laser communication terminal. So here is a photo of laser terminal. The mass is about 5 or 6 kilograms. So first laser communication experiment from a microsatellite to ground was conducted. Here is the transmitted image via optical link. So this is the coast of Australia. So this picture taken by CMOS camera on board was successfully transmitted through the optical link from the satellite. In addition, so we have implemented basic quantum communication function into this satellite. So to an orthogonal, we coherent pulses were transmitted to the ground, and we analyzed polarization of the detected signals. So we confirmed the polarization will be kept through the trans-atmospheric path from the LEO satellite. So this was published in Nature Photonics. So we conducted many international collaborative experiments with CNES and DLR and CSA and NASA and so on. So among them, so CNES team tried to establish optical link with adaptive optics. So left-hand side, so this shows a little bit deformated image, but with the adaptive optics, the spot could be really sharp, like this. So the possibility to use the adaptive optics for SATCOM was confirmed. And here shows our terrestrial free space optical communication network. We developed 3 optical ground stations in Tokyo, in Kashima Prefecture, and in Okinawa. And also we developed 10 sensor stations throughout Japan. So we are now studying real-time measurement and data collection for site diversity purpose. Here shows Okinawa station. So this container can be shifted backwards. Then telescope can track the satellite. So this shows also the same one in Kashima. So these telescopes can be controlled remotely from headquarters in Tokyo of NICT. So this shows a sensor station. So there are several sensors, whole-scale camera, and humidity sensor, and temperature sensor, and pressure sensor, and so on. So in order to show the effectiveness of the site diversity, so this chart shows the probability of laser communication between small optical transponder experiments. So as I shown, so this was done by using this LEO satellite. We examined the same orbit, but we analyzed this data offline. So if we could use only Okinawa station, the availability is 30%, and the Kashima and the Kogane availability were also about 50%. On the other hand, by using recorded data, so if we could use the two ground stations, the availability will be 77%. And also, if we could use a three ground station combination, so availability between LEO and ground, so maybe 100%. So in spite of weather conditions such as clouds and rain and so on. So this data was analyzed during rainy season in Japan in 2016. So this shows the effectiveness of the site diversity. And also this year, April, a small optical link for ISS called the SOLIS experiment was conducted successfully. So Sony Corporation, they have developed SOLIS laser communication terminal, and this was on board ISS. And we provided optical ground station like this. So 1.5 micron laser communication experiment was successfully conducted with the Ethernet protocol. And also, this is VSOTA, very small optical transponder mission. So this satellite is called LiveSat, developed by Tohoku University. We delivered laser driver and collimator connected with the optical fiber. So the mass is only 700 grams. So, but there is no gimbal system. So satellite has to track the ground station by body pointing like this. So this satellite was launched last year. So we are now conducting this experiment till now. And also, in the future, we want to establish more than 10 gigabits per second link between a CubeSat and the ground, or CubeSat and the satellite. So we have studied about this mission. So here is the CAD model, and orbital calculation and optical design were conducted. And also, this is a current ongoing project for high throughput satellite. The satellite communication is aiming for high capacity with lower cost per bit from Ku band and Ka band. So needs for airborne and ocean usage are increasing. So high-speed, large capacity, high throughput satellite needs more than tens of gigabps. But this data rate cannot be transmitted via only RF. So that's why data communication is really attractive all over the world. So currently, Inmarsat 5, they are in service already, and capacity is around 10 gigabps. But in the future, Viasat 3, they are aiming for 1 terabps by using more high throughput satellites. But more future, we are now thinking the hybrid HTS will be needed, including K-band link and optical feeder link. So because of lack of frequency resources in the future for RF band. So then we propose next generation high throughput satellite. So we want to provide 100 megabps plus mobile satellite communication link to mobile users at Ka-band. And the traffic can be controlled according to the traffic of the communication and the location of the users by using digital beam format and digital channelizer function. So if we can imagine if 10 users will use 100 megabps link, the total capacity will be easily reached to 1 gigabps. And if 100 users will use 100 megabps, so total capacity can easily reach to more than 10 gigabits per second. So this data capacity cannot be transmitted by RF only. So that's why we implemented optical feeder link to this link. So we are now aiming for 10 gigabps between geo and ground. So NICT is now developing a data communication terminal on board Engineering Test 9. So we want to realize 10 gigabps between ground and the geostationary satellite. So we want to establish a new screening process from terrestrial optical devices, code path, to space qualified components. So here is the optical part, and here is a 10 gigabps modem part. And in JAXA, they plan to have a Japanese data relay system called JDRS. So these satellites will be launched 2020 or later. 1.5 gigabps optical link from Earth observation satellite to ground via JDRS is considered. So here is the summary of space-based data communication program in the past and the future. So there are many demonstrations in Asia, US, and Europe. So today I summarize these applications individually, and I can say we can categorize these data communication programs into 5 areas. This shows the number of satellites. This shows the service type. So you can see one is a short duration mission like SOTA and OCSD by Aerospace Corporation and so on, by small satellite. And this one is a promising application for geo data relay, like JDRS and NASA LCRD and EDRS by ESA and so on. And there are several venture companies, Skyroom and Space Union and so on. And the biggest application is broadband satellite communication, including Starlink and Amazon and Chinese massive video and German Clear Connect and so on. So some programs were cancelled due to budget issues and so on. And the fourth one is all optical communication program, like laser light communication and laser fleet in China. And also the last one is cyber security, like QKD and so on. So there are also several venture companies, Arcade and Keynet, Canada, and so on. So this is the image of the major application for space laser communications. LEO constellation broadband satellite communication is, I think, growing. And the short duration mission by small satellite and geodata relay service as a promising object. And cyber security with QKD. And also optical feeder link technology for a hybrid high throughput satellite system, as well as deep space link here. So optical communication will be used for many applications in the future. So let me conclude as follows. So recent trends of space laser communications for micro and CubeSats and the mega constellations were introduced. So after the successful demonstrations of SOTA and Aerospace Corporation OCSD missions, the laser communication has been recognized as an important technology for micro and cube satellites. So it is difficult to have enough RF bandwidth under the many satellite constellation environment in the future. So satellite communication, laser communication is expected because of no radio regulation. So space laser communications will be a solution to achieve the higher data rate compared with RF communications and deserve the space cybersecurity in the future. So thank you very much for your kind attention.